So how many have this question, like how can you make teaching come alive and be more engaging? Yep. So you must have thought about it sometime when you were taking the course or when you are delivering a course. So this is a question which is mostly asked. And there are a lot of solutions to this. And these solutions depend on the course you are taking or at the number or the student who is taking the course. Like every student has a different way of learning. In this presentation, I will be presenting to you one such tool which we have developed to make teaching come alive, which is called Wolfram Virtual Labs. And this the lab which I will be going through today, we developed this along with Professor Matteo from Politecnico di Torino in Italy. In this presentation, I will talk to you, I will discuss what are these virtual labs, like why we created these virtual labs, and I will go through an example of how this look like, and I will present the resources where you can go and learn more about it. Yes. So during the last few years, during our discussion with various teachers, professors, and students, like Professor Yehuda, who is sitting over here, Professor Matteo, and various other professors, we were asking them how can we make use of system modeler or Mathematica and make education come alive. And during those discussions, we had several points, and out of that, 3 points were kind of common in all those discussions. The first was the professors wanted some example which are just not a code snippet, like it's just not a manipulate, but they wanted a workflow so that when you go through it, you understand what's happening. So I will go more into that when I present the virtual lab. The second thing was if a professor is developing a course using Mathematica and System Modeler, they wanted a platform from where they can share it with other teachers and students. And the last thing was they wanted to create such materials which can be easily implementable in the classroom. So a teacher doesn't need to take the pains to improve it or to modify it as per the course requirement. So based on this three major background, we did some brainstorming, and we thought, okay, how can we make the complete use of the Wolfram tech and the teacher's requirement, and how can we develop something new? And before we started to develop this virtual labs, we decided to focus on 3 key values. Like we will develop some materials which make teaching come alive, which are adaptable to any course. And third, we will develop courses which will cover the whole curriculum. Generally, the perception about system modeler is it is used in physics or in mechanics, but it is not the case. It can be used over a wide range of courses. And through this virtual labs, we want to present how it can be used in different fields. To demonstrate that, I will be going through the first virtual lab library called College Thermal, which has 2 virtual labs on room heating and on refrigeration cycle. You can download this from the Wolfram modeler, from the System Modeler library store. So when you download this library, traditionally, when you download a system modeler library, it is in the form of an SMA. But for this virtual labs, when you download this library, you will get a Mathematica notebook. In this notebook, as you can see, we begin by a general introduction to this library, and then we present the 2 labs which we are presenting in this library, which is room heating and refrigeration cycle. For each lab, we give a brief description of what the student will learn at the end of the lab, and then we present the final manipulate, which the student will be using in this lab, so that a student knows what he is going to get after reading this lab. So So you get this library notebook, and whichever lab you like to try it out, you can just hit try the lab. So when you click try the lab, the system model file is automatically downloaded and installed, and everything happens automatically in the background. So as a student or as a professor who is new to Wolfram Tech, you don't need to know anything about system modeler or Mathematica and how it works. You don't even need to know you don't even need to know Shift Enter to evaluate an expression. We have automated that to that level. Before I proceed and explain one of the labs, let me tell you, what do I mean when I say make teaching come alive? So we have approached this value through mainly 3 points. The first is as you know, seed to harvest. So we start with very simple models, and we start adding more complexity to that. And at the end, we have a complete or a non-trivial model. Second, when we develop this, when a student goes through these labs, we present them various manipulates through which they can compare different scenarios. Third, we use dynamic tools of Wolfram Tech to create this courses more interesting. Now let me show you how this lab looks like. So this is one of the lab of college thermal, room heating lab. We start with a brief introduction of what this lab is about. For instance, here we give the big picture that at the end of this lab, you will be able to model the internal temperature of a room for any given ambient condition. So a student knows, okay, once I finish this lab, what I'm going to learn and how can I use it in real life. So we first start with giving a top-level view of that. Then we give some objectives which are relevant to the course he's taking, and this is based on the teacher's feedback. Like all these labs we develop in collaboration with professors and teachers. So these objectives we get from the professors. And once you know what are the objectives you're going to cover, we start by modeling simple components. For instance, in a room model, the wall is the simplest component. So we first model the wall, then we go on and add more complexity, and at the end, we combine everything and create the room model. In this presentation, let me show you what we do in exercise 1. Yeah.
When he says we develop models, in the course you don't develop the model.
Yeah, yeah.
You have developed the model for the course.
Yeah, yeah, yeah.
You use the model.
Yeah.
It's not just so you understand.
Yeah, yeah. So just to make it clear, just to make it clear, the student don't need to develop these models. These models have been developed. The Mathematica models and the system model models have been developed and are readily available for use. So a student doesn't need to make these models. They will only use these models to know more about the system, right? So in this wall model, what we can see here are 3 thermal conductor layers, and these are insulation, brick, and insulation layers. And we are giving 2 boundary condition, which is the ambient temperature and at the end, the inside room temperature. So this is the first simple model we start with a very simple model of a wall. Once a student is introduced with this model, then we give a brief description that what are the parameters which are important in this model. For instance, in this model, thermal conductivity and thickness of the wall is more important. Then we present a manipulate where we keep the thickness as constant. Here, the thickness of the brick layer, which is the brick layer, and the insulation layer is like 1 meter, 3 meters, and 1 meter. So in the ratio of 1:3:1. So we present that, and as a student can see, for the normal thermal conductivity values of these layers, you can see the temperature increase across the insulation layers is more, whereas the temperature increase across the brick layer is less. It is kind of not that intuitive that you have a very thick brick layer, but still the temperature increase across this brick layer is minimal. So a student can get a perspective of how these parameters affect the real life design of walls. And
Critical comment. I don't see anywhere mentioned that the solution you're using is steady state, correct?
Yeah.
Otherwise you would have the linear distribution.
yeah, it's a steady state solution we are presenting here. And a student has, like for instance, if a student wants to use a different insulation layer, which might have a different conductivity value. So let's change it to 0.31. And then you can say at steady state, how the temperature increase takes place across various layers. So they can tweak in different insulation values, and they can plan how the wall should be modeled. Subsequently, we then introduce a bit more complexity to our simple model by adding a convection element at the boundaries, and then we present them how the temperature distribution takes place. Here, I must admit, we have taken a constant boundary thickness of 10 centimeter, but it will change in real life based on the fluid velocity across the walls. So here we add more complexity, and we show that there is a nonlinear behavior at the boundaries. So in this way, we start adding more complexity to the model. Similar to what I discussed in exercise 1 of designing a wall, in the subsequent exercise, we design a window, side wall, and other room components such as floors, roof, and people. So these are all pre-made by us. We just explain how we did that, so a student can replicate if they want to. And then we combine all the simple models which we created before into a room model. So this is a system model of a room where it's a model of a single room where we have 4 layers, floor, roof, and people to represent the heat gain inside the room. And we are considering the thermal mass inside the room as a heat capacitor. So for a fixed ambient temperature, we see how for a fixed outside temperature of, for say, minus 10 degrees centigrade, we show that if the initial temperature is 20 degrees centigrade, without any radiator, how the temperature inside the room gets stabilized after a certain interval of time. So this is without a radiator, because inside a room, 10 degrees centigrade is not at all suitable for habitation. So then in the exercise for modeling the radiators, we model the radiator using as an electric radiator, or as a water radiator. So we have those 2 architectures, but I will not go that in this presentation today. Let me show you the most important part of this model, in which we use Wolfram alpha to get the temperature data of one winter day in Rome. So you can see it's a 9-hour data starting, and the minimum temperature is 6 and maximum goes to 11. So this is how a temperature profile of one day in Rome looks like. We then feed this temperature data to our room model, and you can see how the room how the thermal conditions inside the room behave. Here, the green line shows the outside temperature. The blue line is the reference temperature, which a user sets, and the orange line shows the temperature fluctuations inside the room. And the blue line here shows the on-off cycle of the radiator. So you might try to relate with the on-off cycle of the radiator with this temperature fluctuations inside the room. So this is for a 9-hour period. We also, for this given set of parameters, we also calculate the different energy and power consumption in this model. For instance, you can see for this configuration, we have an energy consumption of 37 kilowatt hour. So if a student wants to see how a simple change in setting the reference temperature by increasing the reference temperature by 1 degree centigrade has an effect on the model. So now you can see the energy consumption increased to 53 kilowatt hour. So there was a change of, I think, around 15 kilowatt hour by just increasing the reference temperature of 1 degree centigrade. So we want students to understand that how their choices has an effect on the energy consumption. A student might want to also correlate this change in energy consumption to the carbon dioxide emission and to climate change if they want to. But we present how they can use the equations to understand a bigger concept. So in this short presentation of the room heating lab, I showed you how we used this philosophy of a complete workflow going from trivial to non-trivial model. I showed how we compare scenarios and how we use interactive materials for that. Next important thing is, how do we make this adaptable to any course? So these virtual labs which I showed you are open educational resources. And by that I mean we provide all the system modeler models which we used to create these labs. For instance, in the room heating lab, these are the components which you used in the room heating lab. If you're a professor and if you want to extend this example by introducing one more room, what I showed you was a single room model. If you want to combine 2 rooms and you want to check the behavior, you can use this already pre-made components and expand your models. So you have the ability to increase upon or to change as your course requires. Second, if you are a teacher not familiar with Mathematica, we have teacher materials on request, in which we go through how you create manipulates using system modeler in the background. So if you are a newbie to Mathematica, it will help you to create interactive contents. Next important thing was we have an objective to cover a wide range of curriculum to explain how system modeling and Mathematica can be used in different fields, not in a particular physics or mechanics silos. And for that, we are developing these courses not by ourselves, but in collaboration with professors and teachers. For instance, we developed college thermal with Professor Matteo from Politecnico di Torino. We also have high school chemistry and high school biology, which we developed in collaboration with professors from Linköping University, where Wolfram Math Core is settled. And we have other courses in the pipeline, such as college biology, high school physics, and various other courses, which will be released within 2 or 3 months. We are working hard on them. Next is resources. We have, if you want to use these labs, you can go to the System Modeler library store. And in that, we have 3 labs which are live right now: college thermal, high school chemistry, and high school biology. Before using the lab, if you want, once you go to the lab, you have examples. For instance, we have room heating and refrigeration cycle. Before using the lab, if you want to know what I'm going to see in this labs, you can click on the example, which will take you to the example pages. So it will give you a brief introduction of what we are trying to do in this lab, and you feel if it is relevant to your course, or you can tweak it in a bit to make it suitable for your courses, you can go through these examples. We also released a blog, I think 1 month back, which goes through, this is a blog I wrote in collaboration with Professor Matteo, where we completely go through this lab and explain you how this lab works, and also the experience of Professor Matteo when he developed this labs in collaboration with us. So these are the 3 resources which we have for you. Also, we are creating videos where we go through this virtual labs and explain you how we develop this, how to use this. Those videos will be live in 2 or 3 weeks after the conference. So these are the resources which we have for you. And if you as a professor or an enthusiast who is an expert in a field and who wants to contribute to the community by creating interactive contents for students, you can contact us. We will help you in developing these labs. you can send us, you can meet me after this conference or after this meeting, or you can drop us a mail at virtuallabs@wolfram.com. So before finishing my presentation, I would reiterate on our key values. We want to make teaching come alive. We want this courses to be adaptable to any course, and we want to cover the whole curriculum. And with this, I would like to conclude my presentations, and now I can take any questions if you have. Thank you.